for the introduction. And first of all, I would like to thank the organizers for giving me this great opportunity to give a talk here. Well, today I'm talking about the formation of large-scale zonal flows in two-dimensional turbulence on a rotating sphere. And this is the menu of the day, today's menu. First, I would like to introduce two-dimensional Navier-Stokes turbulence on a rotating sphere and quickly explain what happens in that system. And then I introduce you the basics of Rossby waves, which will be used throughout my talk. And the main part of my talk, nonlinear interactions of Rossby waves and zonal flow formation flows. So let's start. Well, the system I'm mainly interested in is the two-dimensional flow on a rotating sphere. So please imagine a rotating sphere, and we have very thin fluid film with infinitesimal thickness, and we consider flow dynamics in that thin film. I'm interested in this system in terms of the characteristics of the solution of Navier-Stokes equation itself. And also I'm interested in the inhomogeneous and anisotropic structure formation, which is a zonal flow formation, precisely. And also I'm interested in this system in relation to planetary atmospheres and oceans, because two-dimensional flow on a rotating sphere can be a foundation of more complicated and realistic mathematical models for these things. And also, I'm interested in the system in relation to plasma physics through Hasegawa-Mima equation. We consider a spherical geometry in this talk, but if we consider tangent plane approximation, which is called beta plane, then the obtained equation motion has the same mathematical structure to Hasegawa-Mima equation, which is used in plasma physics. So, these are the equations that we normally use to investigate two-dimensional flow on a rotating sphere. We have two-dimensional Navier-Stokes equations here. These equations are written in longitude and latitude coordinate, and U and V are longitudinal velocity component and latitudinal velocity component, respectively. So we have the time derivative of the flow velocity component, and we have advection term here, the nonlinear term, and we have rotation effect here, and pressure gradient, dissipation, and forcing. And these are two-dimensional Navier-Stokes equations, of course, coupled with coupled with a continuity equation. So we have three equations, but if we introduce string function, these three equations can be compiled into one vorticity equation. So normally, many people use this kind of non-dimensionalized vorticity equation on a rotating sphere. This is equivalent to the use of Navier-Stokes equations plus continuity equation. And again, this is written in longitude, and in this case, sine latitude coordinate, and the omega here is the rotation rate of the sphere. And psi is the string function, and zeta Laplacian psi is the vorticity. And this is the advection term, the nonlinear term, and this is written by the use of Jacobian operator. And this is the rotation rate of the sphere, where omega is the rotation rate of the sphere, and we have dissipation and forcing. But in this talk, we would like to omit the dissipation term and forcing term. The reason of omitting the forcing term is just to consider as simple case as possible. And the reason of the omitting this dissipation term is that it is suggested that existence of vorticity is not essential for the zonal flow formation in this system. So we just use this part equals to 0 in this study. By the use of, so in this system, if we start from random and uniform initial condition like this, so this is the velocity field at t equals to 0, we have westward circumpolar large-scale zonal flows after a sufficiently large time. Here, blue color corresponds to westward flow, and red corresponds to eastward flow. And we see very large, strong westward zonal flow around both poles. Oh, we don't see this part. I'm sorry, we see here. And unfortunately, you can't see this part because I have tilted the sphere, but we also have this kind of westward large-scale zonal flows here. And this is the temporal development of zonal flows. And the horizontal axis is time and vertical axis is latitude. At t equals to 0, we don't have this clear structure because we have started from the random and uniform flow field. But soon we see blue colors here. So this means that we have large-scale westward circumpolar flows at t equals to 1 or 2. And these zonal flows develop as time goes on. And after sufficiently large time, we have this kind of flow profile. We have very strong westward flows around both poles. And lots of studies being done in order to understand the mechanism of the formation of zonal flows. But unfortunately, the mechanism of large-scale zonal flows formation has not been made clear yet. So today I would like to introduce our trial by using the nonlinear wave interactions of Rossby waves to understand this phenomena. So let's go on to the Rossby waves. In this system, we have linear solutions called Rossby waves. And this Rossby waves got this kind of form. Here, this y is a spherical harmonics, and this omega is the frequency of Rossby waves. And as a function, any function on sphere can be expanded by spherical harmonics because spherical harmonics are the perfect sets in the spherical geometry, like this. So this means that dynamics of Rossby waves determines the temporal variation of the flow field completely. So this also means that three-wave nonlinear interactions of Rossby waves are very important to understand the time variation of two-dimensional flow on a rotating sphere. So we investigate the zonal flow formation from the perspective of three Rossby wave nonlinear interactions. In order to do that, I next briefly introduce the zonal Rossby modes and conditions for nonlinear interaction and resonant nonlinear interactions. As I have told you, that the Rossby waves can Rossby waves dominate the flow field dynamics. So there are Rossby waves that are in charge of describing zonal flows, and which will be called zonal Rossby modes in this talk. And they are the Rossby waves with superscript equals to 0. For example, if we only have y20 mode, then the flow field becomes like this. Here we have one very large westward zonal flow and one very large eastward zonal flow. So we have two zonal flows for this case. And if we consider y30 mode, then we have this kind of three zonal flows. So the development of the zonal flow is equivalent to the energy accumulation to yn0 zonal Rossby modes. This is the energy spectrum at t equals to 0 of the flow. We see random and uniform energy distribution around here. But after sufficiently large time, for example, at t equals to 10, we have energy spectra like this. Here the horizontal axis is a total wave number, which is the subscript of the spherical harmonics. And the vertical axis is azimuthal wave number, which is the superscript of the spherical harmonics. And we see that energy is accumulated to the m equals to 0 mode, the zonal Rossby modes. And this energy distribution is corresponding to the circumpolar large-scale westward zonal flows. And please keep this in your mind for a while. So In other words, the purpose of today's talk is that we would like to understand the energy accumulation to zonal Rossby mode with low n, the total wave number n, from the perspective of three Rossby wave nonlinear interaction. So next I would like to show you the necessary condition to realize three-wave nonlinear interaction of Rossby waves. So we have two waves, wave B and C, interacting each other and giving some effects on wave A. And in order to have this kind of this nonlinear interaction, we have to have these conditions satisfied. This is the condition for the superscript M, and these are the conditions for the subscript N. And if we have additional one condition satisfied, which is the condition for the frequency of Rossby waves, this means the sum of the frequency of wave B and C is equivalent to the frequency of wave A, then this nonlinear interaction is called as resonant interaction. And this resonant interaction is considered to be very important interaction in this system because we have this very clear theorem. This theorem says that when the rotation rate of the sphere is infinitely large, then flow dynamics is totally governed by three Rossby wave resonant nonlinear interactions. So, resonant interactions should be the type of interactions that works most strongly in our numerical calculations that where we have large-scale zonal flows. So these are the things I would like to know in order to explain my main part of my talk. So in the next, in this part, I would like to show you what kind of three Rossby wave nonlinear interactions are the direct factors in the formation of large-scale zonal flows. And here I introduce you two types of nonlinear interactions, near-resonant interactions and non-local interactions. And I will talk about this one by one. So let's start with the near-resonant nonlinear interactions and the large-scale zonal flow formation. As I have told you that this energy distribution is corresponding to the westward large-scale circumpolar zonal flows. But if we enlarge this part, we can easily notice that the energy accumulated part is not the solid line, but the dashed line. And in fact, energy is accumulated to only zonal Rossby modes with odd integer n, not even integer n, only odd. And if we plot the sum of the energy of zonal modes only with n equals to odd integer, or only with n equals to even integer, we can notice that the zonal Rossby modes with n equals to odd integer obtain much energy, whilst zonal Rossby modes with n equals to even integer do not obtain any energy. So the energy is accumulated to zonal Rossby modes whose n is low and odd integer n to realize this flow structure. And we believe that this can be a clue to clarify the zonal flow formation mechanism. And we would like to think about this now. And speaking of dependence on the parity of n, one important thing that we can think of is the three-wave resonant interaction. These are the conditions for resonant interaction that I have shown you. And by using this, we can classify all the Rossby waves, whether they can be a member of resonant interaction, at least one of the resonant interactions, or not. And by doing that to zonal Rossby modes, we can notice that zonal Rossby modes having n equals to odd integer can be a member of resonant triad. So they are the resonant zonal modes, which is the resonant zonal modes. But zonal Rossby modes having n equals to even integer cannot be a member of resonant triads. So they are not the resonant zonal modes. So the energy accumulation is accumulated to resonant zonal modes in our numerical simulation. And if we recall that resonant interaction is dominant in our numerical simulation, and if we also remember that only resonant modes develop in our numerical simulation, then some of you, including me a few years ago, may think that we might be able to explain the zonal flow formation only by using resonant interaction of three-wave Rossby waves. But unfortunately, it cannot. Because if we consider the detailed balance of energy, it can be easily shown that no energy is transferred to zonal modes by resonant interactions. So unfortunately, although the resonant zonal Rossby modes obtain energy, but it is not done by resonant interactions somehow. So the next thing that we may think of is, then how about near resonant interactions, which may have a very similar or close properties to resonant interactions. So near resonant interaction cannot satisfy this condition, but instead we have this here. So this value is quite similar to this frequency. So we would like to check this point. But unfortunately, we don't have clear definition for near resonant interaction as far as I know. So in this talk, we define near resonant interaction by using this condition. This means that the omega, the frequency of wave A minus the frequency of wave B plus C is almost equivalent, is almost equivalent to 0, but not exactly 0, and having very small value. And we define the threshold for the near resonant interaction by using the Rossby number. And the Rossby number is defined by the use of rotation rate of the sphere omega and length scale and velocity scale of the flow. And by using this definition, we see time derivative of energy of zonal Rossby modes only caused by near resonant interactions, or the time derivative of energy of zonal Rossby modes only caused by purely non-resonant interactions. And in order to calculate this, of course we have to calculate these things, and this part can be calculated if we know the nonlinear interaction coefficients, and these nonlinear interaction coefficients can be calculated by the use of these notations given by Silberman. So we calculate this H first, and we use flow field data for this spectral data of string function here and here, and we get this and see these. Okay, and before going to the before seeing the result, please recall that the energy spectrum energy distribution corresponding to this flow field is something like this. So we only have strong energy accumulation to zonal Rossby modes with low and odd integer n. And this is the result. Here I am showing you the temporal mean of time derivative of energy of zonal Rossby modes caused by only near resonant interaction or non-resonant interactions. And here, near resonant interaction is the green. It is pointed by green color, And we have 3 time range here. This is from t equals to 0 to 0.3. This is the very beginning of the numerical time integration. And this is t equals to 0.3 to 0.6. This is the middle stage of the formation of zonal flows. And this is t equals to 0.6 to 0.9. Here the zonal flows become visible. And in all time stages, we see very large value for green, which means a near resonant interaction. And we don't see non-zero value by non-resonant interaction. So this suggests that only near-resonant interactions are directly sending energy to circumpolar large-scale zonal flows. So this is the first result I would like to show you. And then next, let's go on to the local nonlinear interactions and large-scale zonal formation. Here I would like to show you the energy spectrum of the flow at certain times. For example, this is t equal 0.1, 0.3, 0.5, 6, 7, 8. And if we see these closely, we can notice that zonal energy corresponding to the circumpolar flow, something around here, first appear at very low wave numbers. So we have strong energy distribution around here, but then instead of appearing this region, the zonal energy corresponding to the circumpolar flow first appears here and here, and then slightly going up. And this suggests that we have energy transfer to circumpolar flow non-locally. So we would like to check this point next. But unfortunately, again, we don't have the clear definition of non-local energy transfer, non-local interactions. So this time we use this definition. This means that, for example, we have 3 waves here, and these waves B and C are interacting each other to give energy or to give influence, to effect on wave A. And if when we are considering non-local interaction, that means the wave numbers of wave B and C and wave number of wave A have a big gap. So if NB minus NA in this case is more than 40% of NB, then we call this interaction as non-local interaction in this talk. And again, we see these things caused only by non-local interactions or local interactions. And these are the results. This time, please pay attention to blue color, because this is a non-local interaction. And again, we see very strong values for low and odd integer n only by non-local interactions. And we don't see energy transfer to these parts by local interactions. So these suggest that only non-local interactions are directly sending energy to circumpolar zonal flows. And this is the second result that we got. But so far, we now know near-resonant interaction and non-resonant interaction are the important things for the formation of zonal flows. But they are the totally different concepts. So maybe we have to see the value, this value caused by non-local and near-resonant interaction, and non-local but not near-resonant interaction, near-resonant but not non-local interaction, and neither near-resonant nor non-local interactions. And these are the mean value of time derivative of energy of zonal Rossby modes by these 3 types of interactions. And we see almost zero energy transfer to the large-scale zonal Rossby modes by these interactions. So they are not the major ones, to form the large-scale zonal flows. But if we see non-local and near-resonant interactions at the same time, then we see a very strong value for n equals to odd integer. N is low and odd integer in these three time range. So this means that the set of near-resonant interactions and set of non-local interactions coincide in this system, and the energy is non-locally transferred to large-scale zonal modes by near-resonant interactions to form large-scale zonal flows in the system. And this is the summary. So in unforced two-dimensional turbulence on a rotating sphere, we have formation of large-scale circumpolar westward zonal flows, but the mechanism of zonal flow formation is not well understood. So we have closely investigated the non-linear interaction of Rossby waves and found that non-local energy transfer to large-scale zonal modes by near-resonant interactions is important one. And well, the importance of near-resonant interaction is, I think it's natural agreement with the intuition because we know that the resonant interaction is very dominant in our system, but they cannot send any energy to zonal Rossby modes. Then maybe the next thing we think about is near-resonant interaction. So this is very natural. And importance of non-local interaction may be strongly related to the compactness of the flow field domain. When we consider beta plane, so the plane approximation, and it's sometimes considered that beta plane is an infinite domain. And in that case, the flow field is not compact. But in this talk, we consider spherical domain. Then this is, of course, the compact domain, so that the basic modes are discrete. We don't have continuous modes. So the nonlinear interactions must be non-local, and this tendency is stronger in the low wave number region. That's why we have very big gap between wave B and C and A, and we have non-local interactions. So in numerical simulations, of course, it happens that non-local near-resonant interactions work strongly due to these geometric constraints. But it also happens that flow field evolves in time to form, or from the random and uniform initial condition to form the state where the non-local and near-resonant interaction dominates at the same time. And understanding the mechanism of this part and knowing what kind of nonlinear interaction is controlling this process is my, I think, my future work. Thank you very much.
Okay, thank you, Kiori. Questions?
Hi, I don't know this field at all, but I was trying to understand the basis for your neglecting dissipation. If you're thinking of a thin layer of fluid on a spherical body, apart from momentum transfer naturally in the tangential directions, there's also the fact that the fluid is in contact with whatever, with the earth or whatever it happens to be, and momentum loss in that direction would also be important. So, what range of length scales is it okay to leave out dissipation? I'm sorry if it's an ignorant question.
Okay. First of all, there is a very maybe I only can answer the for the horizontal direction, not the vertical directions. But first of all, we have a very famous theorem called non-acceleration theorem, and that means that zonal flow is accelerated by the viscosity dissipation. But that theorem is derived by the weakly nonlinear analysis. So, so the result of the weakly nonlinear analysis is not always applied to the fully nonlinear system. So we first tried showing that the implicit limit solution and the implicit solution coincide in this system, and we could do that. And after that, we performed series of numerical simulation in order to know the implicit limit flow. And then we confirmed that the in the implicit case and implicit limit case, we also have a completely same flow structure. So I'm sorry, I still don't know the mechanism of still don't know why we can really ignore their dissipation, but at least we could show that point.
Okay,
So,
thanks.
so that's why I.
David,
You understand in a simple way why in this system you only get jets near the poles? I mean, we're used to seeing simulations which presumably are forced and have dissipation where you get a whole slew of jets, but you're only getting these strong jets at the poles in yours.
Yes.
Is there a simple explanation for that?
Yes. When I was a student, I was doing a forced system, forced problem. And in our case, of course, we have a zonal band structure or very large, a few zonal flows. But I found it that's a little bit too difficult for me to understand, fully understand. So I came to this enforced system. And after investigating this enforced system, I noticed that so in first system, we have this kind of flow field, and in unforced, we have this kind of flow field. But if so, they look totally different. But if we see energy distribution, we have very similar energy distribution for both of them. And this can move on to very, very large 2 or 3 zonal flows. And when shifting to this type of flow field, this energy distribution is changing into some other type. But for both cases, at first we obtain energy accumulation to low and odd integer zonal Rossby modes with low and odd integer n. So, well, I'm not sure if this can be answer to your question, but so that's why by understanding this problem, it can also give some kind of some
I guess I was just saying, do you have a, I don't know if there is, but is there a sort of simplest explanation of why, I can see they're both driving zonal flows, but why one of them drives a zonal flow which is only at the poles and the other has a band of zonal flows? Is there a simple explanation?
Simple explanation. Okay, so this is something like 1 to 15. And the Rossby mode, the combination of Rossby modes and realize this kind of flow field because they cancel in mid to high, low latitude. And for this, we have maybe something like 7 or 9 or something like that. And then the cancellation in this region is not working in this case. And as a result, we also have zonal flow. We see the zonal flows around here.
okay, this gentleman. Yeah, you.
Can I ask about the near resonant interactions for n even?
Near resonant interaction.
N even.
N even.
So you don't see any of those, is that correct?
No, we don't. So
So what is the reason that any...
I try to explain it very easily. We have huge amount of interactions, of course, and for both n even and odd, we have non-zero effect to the zonal Rossby modes. But for both cases, large cancellation occurs. And for n even case, most of them cancel out. And for n odd case, most of cancels, but some remains. And we have that kind of result.
Do you understand that at all? I don't understand why n even you don't get for first.
No, this is something I would like to, I need to clarify, but somehow for n even case, the effect to y in zero mode from huge amount of three-wave interaction cancel and disappear.
It's not each resonant. No energy. It's the cumulative sum.
So we have triad like this, and this is wave A and BC. But we also have this kind of triads, and we have to add all the effects to for this. And by adding all of them, somehow for the n equals to even case, they just disappear.
Identically. Zero.
Almost zero.
Almost zero.
Yes, almost zero at each time. And after, so we have two types of cancellations. At first, they cancel at each time. So we have almost zero energy transfer at each time. And then they tend to take a positive and negative value depending on time. And after integrating long time, we have zero effect at the end.
I'm a bit rusty on my Legendre polynomials, but does n even have some symmetry about the equator?
Yes.
What
And
is it?
in odd case, we have anti-symmetry.
Thank you.
All right, I think we're running, Guillaume was next.
I was wondering if you had a physical picture as to why you needed this small mismatch and what it would mean physically. Because the resonant part does not drive directly zonal flows. You need a near resonant, so you have a small mismatch. That is a very important physical thing to understand. So did you understand it?
Unfortunately, I don't really know the reason why, the physical reason of the importance of near resonant interaction. I have just found out that near resonant interaction is working. So maybe the next thing that I need to know is the physical importance of the near resonant interaction. Sorry about that.
I'm going to sneak in a follow-up on that because I had this similar concerns. Really two things, how near is near?
Yes.
And if you were trying to build a model,
Yes.
how would you construct, I mean, you're going to need a resonance broadening in the three-wave propagator.
Yes.
What's the model of the resonance broadening that
Yes.
you're pointing
Yes.
toward?
So I had no time, so I didn't show you, but we have calculated this something similar, but non-local and near resonant interactions, but we gradually change the degree of near resonance and see what happens. And unfortunately, at the moment, I haven't found any clear thing that I can tell you. So.
All right, Benjamin.
So the results are echoing an ongoing debate in the rotating turbulence community, so not 2D but 3D, where you have a very similar problem where you try to understand the emergence of geostrophic flow, so low frequency depth invariant flow with inertial waves. Of course, Rossby waves are type of inertial waves, so I think there is a connection there. And so people have also argued that near resonance are very important. And recently, there's also another suggestion, which is about four waves. Right?
Yes.
Is it something that you consider that maybe?
Yes, I have also considered four-wave resonant interactions, but I haven't found any good result to tell you. I'm sorry.
Okay. So your results are more consistent with near resonance than
Yes.
always is that.
Thank you.
Okay, I think I see a quiescent audience. Let's thank Kiori-san.